Thank you. Okay, so let's sort of very briefly review what we talked yesterday. We talked about matchings under preference. It's a sort of a refinement of what we understand as matching. The vertices have a rank preference over their neighbors. So in this setting, for the rest of the talk, also we will be considering the ordinal setting. So there's a preference list that comes with the input graph. Okay, so I'll be referring to, I'll be mostly talking about vertices, but if I slip and say agents, then do understand that I'm actually still in the graph theoretic setting. Edges are acceptable matches, and so that's sort of the framework we are still dealing with. Now, the problem that we looked at yesterday, the house allocation problem, had a specialty that not all vertices in the graph had a preference. So it was a bipartite graph where one side, the vertices on one side had preferences and the other ones did not. So today we will be looking at instances where all vertices have preferences on them, like they all rank their neighbors in some form. In this context, perhaps the benchmark, the most canonical concept in this setting is the stability. It's stable matching. So what is a stable matching? It's a matching. So it's a set of pairwise vertex disjoint edges in the graph, which does not have certain forbidden structures. So what are those forbidden structures? They are called blocking edges. So vertices, so you can imagine a matching in which some vertices are not matched, right? So we sort of we are going to treat them as if they are self-matched. So being unmatched is as if you're matched to yourself. So it's just a matter of convenience, okay? Because we are in the matching under preference scenario, because they model real life situations where people voluntarily participate in markets in order to receive a match, we will assume that everybody prefers being matched to one of their neighbors over being unmatched. Is that clear? So that's the thing, okay? If you don't get matched to anybody, it's your default scenario is you're self-matched. It's like, I guess, being single. So I think the self-match is a term now being used by some celebrities to define single status, but that's the way it is, okay? So that's sort of the current, so let me just write it. So for any vertex, basically, can you read if I use this font size? So this is defined, okay? So this MV could be another vertex, otherwise it is V itself, okay? This is what I mean. Okay. So keeping in mind that every vertex would like to be matched to somebody over being unmatched, so the preference list of a vertex can be sort of seen as a rank list on its neighborhood set. God, the handwriting is terrible. Can you, okay. Followed by itself, okay? And a blocking edge is one where two endpoints, so blocking edge is an edge which is not part of the matching, okay? So it's always defined with respect to a given matching. For a matching, we say this edge is a blocking edge or not. So an edge which is not in the matching is a blocking edge if the two endpoints, in this case U and V, each prefer each other, meaning U ranks V higher than whatever its current matching status is. And the same for V as well. So it allows the possibility that U is unmatched, but V is matched. But because U is unmatched, obviously U would like to be matched to V over being unmatched. I just said it, right? That's the bottom line. And V somehow likes U more according to its preference, ranks U higher than whoever is this MV. Okay, so that's what a blocking edge is. Is the definition clear? Because this is the absolute basic thing that must be clear, else there's no point. Okay. Sorry? So yes, so the preference list under normal circumstances would be just defined as a rank list over the neighbors. I said now assume as if V has placed itself at the end of the preference list. This just enables us to talk about this meaningfully syntactically also, because then we can say that, okay, V wants to be self-matched or being unmatched as the least of its preferences. If they are neighbors, yes. Correct. So, good point. So the point, so is a blocking edge concept, it's called a blocking pair, blocking edge, so on and so forth. Blocking edge is the common term when we're talking in terms of graphs. Blocking pair would be if we didn't talk about graphs, but just talked about agents and acceptable pairs, okay? So now stable matching is one which does not have any blocking edges. Okay, so these are the forbidden structures. No. Why? I have said nothing about bipartite or completeness. It's any graph. Why can't this be any graph? This is the neighborhood. Does anything materially change if this is not a complete graph or not a bipartite graph? Right? Everything is just an abstract edge relation and agents are treated as vertices. Okay, so is it clear that a stable matching must be maximal? Swap? Is that the definition of maximal? Non-maximal rather? What is a non-maximal matching? But just because an edge is not matched doesn't mean the two endpoints are not matched to somebody else. What is the definition of maximal matching? There cannot be an edge with two whose endpoints are unsaturated. What you're thinking and what you're saying are materially different. It's important. Matched, the property of matching is an edge property. Just because one edge, this edge is not part of the matching, doesn't mean that the two endpoints are not part of the matching. Okay, please understand that. So that basically was the point that he was saying, that if I have an edge, so if I have a non-maximal matching, means there exists an edge whose two endpoints are not part of any matched edges. So then, can this non-maximal matching be stable? No, because that edge itself is going to be a blocking edge. So a stable matching will always be maximal. Okay, so that's one thing. Now, the stable matching problem. So the problem in the abstract terms is treated just as a graph and set of L is a set of preference lists. Okay. This. And the question is, does there exist a stable matching in J? When this graph is a bipartite graph, it's known by its sort of famous name, stable marriage problem. And when it's a non-bipartite graph, it's known as a stable roommate problem. Okay. So, yes. So this as I said at the very beginning yesterday, that the algorithms we will be covering today are really important in economics, and they have been very influential for decades. In 2012, Lloyd Shapley and Alvin Roth received Nobel Prize in economics, and the commendation stated their work on stable matching, as well as the evolution of the TTC algorithm as the reason for this significance. The significance of their work underpinned by these two things and several others. Unfortunately, David Gale had died by then, but I mean, if he had been alive, he would have shared on it too. So this is sort of the thing. Now, why is this important? You should understand that in the bipartite case, as we talked yesterday, it captures many real world problems that you can easily identify: college admissions or any type of centralized job matching situations, any kind of two-sided matching markets is where stable matching comes into play. So there was an algorithm that was being used in New England, in Boston region, for about since the late 19th century, 1800s, for admitting doctors to teaching hospitals, like what you would they call residents, what we would call first-year intern doctors. Okay, and they were basically trying a whole lot of things and heuristically trying to sort of find an algorithm that would give rise to a good solution. And the system was the same thing. It was like students would send in their preferences and so on and so forth. They tried to centralize it and so on. And by trial and error, they chanced upon an algorithm, which David Gale and Lloyd Shapley had analyzed to see whether it was any good at all, like how robust was the matching market. It is that algorithm that has come to be known as the Gale-Shapley algorithm. Now, I don't know how much you know about this. If you've seen in algorithms course, this is one of the standard matching algorithms that is taught. But irrespective of that, it's just something that is very simple to know and understand. So you could easily sort of, if you see once, you will hopefully remember. So this is the algorithm that works for bipartite graphs. Okay, so let's start by I'll not run through the entire example. It's a largish thing, but I'll just say how it proceeds and you'll sort of get the feeling of it, and then we'll prove some correctness results. So here, the matching market consists of what? 5 people. So Victor, Wyatt, Xavier, Yancy, and Zeus, and Amy, Bertha, Claire, Diane, and Erica. Okay, before I start, I should say all these things, the stable matching, stable marriage problem, Gale-Shapley algorithm, these are the work of the 1960s. So the terminology is extremely old-fashioned and supremely dated. So don't be offended. I'm just using terminology that is in practice. At some point, this will all change and we'll become much more sort of sensitive to other things. So this is why matching, as in a bipartite graph, two-sided setting, you want to deal with the most simplest instance of it. It's the marriage thing. College admission, job markets, they become a little more complex because employers don't hire one person, right? They hire multiple people. Employees typically go to one. So it's like not a matching in the traditional sense. It becomes a more generalized concept of allocation or many-to-one matching. So a matching, as we understand it, which is like a one-to-one relation, is captured by what is known as marriage. So that's where all this terminology comes in. Okay, having said that, so the thing is, Victor's top preference is Bertha, followed by Amy, Diane, Erica, Claire. Okay, so the 0th, first, second, third, fourth. I know why this starts with 0, but okay. So this is the way it is. And on the women's side is Amy, Zeus, Victor, Wyatt, Yancy, and Xavier. So first, Victor makes a proposal to Bertha. So everybody, it's the men. This is like, we can call it, yeah, can't see. This is what was known as the man proposing Gale-Shapley algorithm, because it's the men who are proposing. This is the part that irritates me the most, but it is what it is. You do the same thing just symmetrically from the women's side, and mathematics will not change. So what happens is each person proposes based on their ranked preference list. Here we are assuming we have a strict ordering. Okay, so at any step, everybody knows who is at the top of their preference list. The person who is receiving the proposal considers it, if this is the very first proposal that they receive, And subsequent to that, as they receive more and more proposals, they consider the current sort of match with the proposal they have just received. If they like the new proposal more than, according to their preference, if they like it more than their current status, then they reject that and move. So the men, because they are proposing, they are sort of moving down their list, and the women who are receiving proposal are sort of moving up their list. Okay, so that's the basic mechanism here. So Victor starts by proposing to Bertha. Bertha, at this very first step, obviously is not holding any proposal, so she accepts it. Okay, so so they called it an engagement, not a marriage, but an engagement. Followed by that, Wyatt proposes to Diane. Again, this is Diane's first proposal, so she accepts. Okay, followed by Bertha again. So now Bertha has to, basically she was having a proposal from Victor, and now Xavier is proposing to her. So she likes Xavier more than all others. So basically she rejects Victor and she moves up her list all the way to the top to Xavier. Okay. Now followed by that, again, it's Amy. So Amy is right. So now, correct. So because Bertha accepts Xavier and Victor is rejected, Victor will now go down his preference list and propose to whoever is next. So basically, what is happening is, as the men are proposing, they are going down their list, they're striking off people from the top of their list. As women are receiving proposals, they're striking off people from the back of their list. Okay, so nobody ever goes back and forth. It's always a linear move from top to bottom, bottom to top. So this continues until either everybody is engaged, meaning every woman, either all the men have received a proposal, have proposed and have been accepted by somebody or another, and nobody has gotten rejected. So the mechanism that keeps the thing sustained is that here, for example, Victor was rejected by Bertha. So Victor had to go down his preference list and start the proposal process again. So he proposed to Amy. Yancy is also proposing to Amy. So now Amy rejects Yancy and accepts Victor. So now Yancy will have to move down his preference list and propose to Diane. Okay, so where is Diane? Diane is here. So yeah, so now Diane rejects Wyatt and moves up and accepts Yancy. So this continues for however long it is needed. In this particular example, the preference lists are complete. Like the graph here would be a complete graph, because everybody ranks, all the men rank all the women in their preference list. This is not necessary. Everything that I've said will work even if the graph is incomplete. However, you do need bipartiteness. Do you see where? Meaning? It's sort of, you're thinking right, but it's a right. So the thing here that we are doing is, if Victor and Wyatt had an edge between them, right? Victor would be proposing to Wyatt, and Wyatt would be receiving the proposal when Victor is proposing, as well as the other way around. Wyatt would be proposing to Victor, and Victor would be receiving. Here, the roles are very precisely defined. The men only propose, and the women only this. So that's where bipartiteness is very intrinsically used, but not the fact that everybody is everybody's neighbor. I mean, it does not need to be a complete bipartite graph. Okay, so I'm not going to run this whole thing, but the final matching that will result from it is this. Okay, let me see, yeah. Okay, so the final would be Victor matched to Amy, Wyatt matched to Claire, Xavier matched to Bertha, Yancy to Erica. By the way, do you see why Xavier got matched to Bertha at the very first step? Correct. So one can show that in any stable matching, these people will always be paired. Can you say why? Use the definition of blocking, use the definition of stable matching. There's only one definition you know of stable matching, that it cannot have blocking pair. If they are not matched to each other, then what will happen? They will form a blocking edge, no matter whom you match any one of them to, right? That's the thing. Now, you don't have to be each other's top preference to be part of every stable matching. It can be that in certain cases you are somebody's second or third preference, and these sorts of edges are called fixed edges, meaning they will always appear in every stable matching. The most obvious fixed edges are things like this Xavier Bartha type situation. Sorry? Yeah, that's the most obvious. But I'm saying fixed edges need not always necessarily have this property that the two people are each other's top preference. They need not be top preference, and still you can be a fixed edge under certain considerations. Okay, so can somebody prove why does this algorithm give a stable matching? It does not. That's what we will prove. Can you just first show, however, that whatever matching it creates, it's a stable matching? Sorry, could you go a little slower, perhaps? Okay, but we don't deal with blocking edges explicitly in the algorithm. The algorithm works by people just looking at their preference list and just very sort of, like it's a machine sort of thing, just looking at the preference list and proposing to the first top available person who hasn't rejected them. Xavier would have proposed to that person before proposing to Amy. Yes. Yes, that's basically the idea. Suppose M is not. So the thing is, if you want to do research in theory, you have to be able to use definition to make formal proofs. The things that you are saying are the intuition. But to make a proof rigorous, you need to be able to use the definition that you know. So is not a stable matching means there exists a blocking pair, right? So this is the only definition of stable matching we know so far. So UV such that U prefers V over whoever his match partner is in U, and same for V, prefers U over its match partner in M, correct? Say U is the sort of A side, the proposing side, okay? Then clearly by Gale Shapley's, the algorithm that I described, use preference list clearly would say that V is ranked higher than M of U, whatever the final matching was. But then, because you got matched to somebody lower, it must be that V would have rejected U's proposal. But V only rejects a proposal when she gets something better. So it she ended up with this matching, but then that means, but this is less than her lesser preference than you. So this couldn't have happened during the matching, right? So yeah. So you understand that, okay. Okay, by the way, the Gale-Shapley algorithm is also like TTC, it has become like a prototype. Lots of people, this is now known as a deferred acceptance algorithm. So there are lots of algorithms that work like Gale-Shapley, where the proposals or the matchings, these proposals or these engagements are basically temporary matching edges, which you are basically tinkering with as time goes by, right? So this sort of a thing is known as deferred acceptance. So if you look at a stable matching literature, the term deferred acceptance algorithm or deferred acceptance style algorithm may pop up. It basically would have something familiar, this familiar flavor. Same thing with TTC also. That type of coalition finding and sort of switching around a cycle is what a TTC style mechanism is known as. Okay. All right. So this is the thing. So what about this? What happened? What about this theorem? Theorem 2. All possible, it's something somebody was saying, all possible executions of the Gale-Shapley algorithm will have the exact same output. It ends up with the proposing side getting their best partner, best stable partner. So that's called, there's a special name for it. It's called this, if suppose we are doing the man proposing Gale-Shapley, this would be the man optimal Gale. It has a special name, man optimal stable matching. If it's a women side who's proposing, then you would get the woman optimal stable matching. So this is what answers your question, that even if in that example, it may seem like, well, we are letting this guy, Victor, propose first, followed by Wyatt and then Xavier and so on, right? Why does Victor get to go first? Maybe if somebody else had gone first, could we have had a different outcome? It turns out no. The exact same outcome would result from it. So this itself, this is a very remarkable result. To say that somehow or another, if I knew what everybody's stable, optimum stable partner was, and I just matched them, just like just pick those edges, the set of edges I get is actually a matching, and not only is it matching, it's also stable. It's not at all obvious to me why just picking people's best stable partner would actually constitute a matching. Right? You and I can both have, like from the definition of blocking pairs, right? Not thinking about Gale-Shapley, that algorithm, it might be that both of us have the same optimum stable pair, stable partner. It turns out it's not. Okay? So can we prove this? Yes? We can. Yes. And it's notable that it has been shown, and it was shown fairly early on, that there can be exponential number of stable matchings in an instance. It's not. Okay. What do I do to sort of get a screen? Okay, so there can be exponential number of stable matchings, but this man proposing Gale-Shapley will always give the exact same outcome. If you use the woman proposing Gale-Shapley, you could potentially get a very different matching. Okay, so if there are at least the instance has at least two different stable matchings, The one that gives the best outcome for the men, okay, that is the one that will result from the main proposing Gale-Shapley. And there's also this other matching. If you did the Gale-Shapley type algorithm from the women's side, then the stable matching that would emerge is the woman optimum stable matching. And while it's not at all clear from what I've said so far, these matchings in a very meaningful and mathematically precise way constitute the maximum and the minimum matchings in some partial order. Okay, and all other matchings sort of fall in between. Okay, so that we won't have time today to get into the details of that. But if you're interested, you can look at that book, the first one. It gives a complete total mathematical exposition on this. Okay, so to get back to this, can we show this, that all possible executions of the Gale-Shapley algorithm will always result in a matching in where each man has the best partner that he can have in any stable matching. So how would this proof also go? I don't know. The point is there cannot exist. See, there are suppose n men. You can potentially have n factorial different ways in which you order the men, and you say that the Gale-Shapley algorithm will respect this ordering. Okay. So I can't possibly. So tell me now, what is it that you will? So there can be this many potential number of orderings. So which two orderings you're talking about is not clear, is what I mean. Okay, again, suppose, say, M is the result of this Gale-Shapley algorithm, okay? And suppose there exists, as a contradiction to that statement, suppose there exists a man, M, let's say, it's just easier to say man, woman, and so on instead of UV, such that there exists M prime, another stable matching. I apologize for my handwriting. It's kind of hard to write. Matching such that M's partner in M prime is better than its partner in M. Okay? Is this clear? If such a thing were true, then it would be a contradiction to the statement of the theorem. Because the theorem is saying that it cannot happen, right? That this person is the best that this man can receive in any stable matching. So this thing cannot happen. Suppose this is true, then how? Which woman? In what? There are two matchings. Okay, consider W prime maybe. This woman, yes. If it is meaning, yes. So it must not, this woman, this W prime in M must have received a strictly better partner. Else W prime and M would block what? M. Correct? That's true. Then, so all it means is therefore W prime's partner in M is better than her partner in M prime, which is M. Now, why? Blocking pair to what? all we are saying, we didn't avoid the contradiction, right? All we know is W prime's M partner must be better than, according to her preference list, must be better than M. And that's a conclusion we have drawn here. Where is the contradiction? Just a minute. So M likes W prime more than his current partner in M, but W prime does the opposite. W prime likes her partner in M more than in M prime. Yeah, somebody was saying something. W prime. So that's the point, right? This is what is W? W is M's. Okay, there are too many M's running around. Let's call it X. Yes, okay. Sorry. Okay. Can you rephrase what you were saying? So your W is, I take M, X is M partner, right? Okay. Then, if you can explain using, you said something. A drawing. Drawings are not pictures. Picture proofs are not formal proofs usually.
If we have like in M, in matching M, if we have like this was a matching, and if M dash, this is a matching. Okay, this is M's list and or X's list, and what we can say is that now if W, this is W and this is W dash. So if both W and W dash, like if basically this isn't crossing, then we can say that.
What is this crossing represent? This itself is W, W dash. What are these to them?
This is W. This is W's preferences, and this is like W dash's preferences. So if basically if they aren't crossing, then we will say that
they will cross. That's the point of it, and they potentially always cross. So the point about it's not maybe clear from what I've said, but this whole thing that the stable matchings have this property that if something is a man optimal matching, which is what it will be if the men are proposing, then that results in the worst stable matching for the women, and vice versa. So the man optimum stable matching is the women pessimal stable matching, and the women optimum stable matching is the men pessimal stable matching. So what that also implies, with some amount of argument, is that both sides, men and women, if X prefers a matching M prime over M, then its partners, especially the woman whom he is preferring, like he prefers this person, Y prime, over Y. Y prime's preference between the matching M and M prime must be the opposite. So the thing that you're saying crossing must happen for from the definition of stability. Okay, all right. So let me just try to sketch a proof for this. Okay, so consider an arbitrary execution of this Gale-Shapley algorithm. Okay, so maybe let's call it E. So I'm going to state a property regarding any arbitrary execution of Gale-Shapley algorithm. Therefore, it holds for every execution. So do you understand how these proofs work? If I assume nothing special about an execution of Gale-Shapley, it means that this, whatever I will prove as must hold true for every execution. Okay? All right. So let's call it E. Okay? So as we see, it's this execution of Gale-Shapley results in this matching that we are calling, let's say, M. Okay? So during this execution, of during this run of Gale-Shapley, X proposes to Y prime, this woman, ahead before it proposes to its eventual partner Y, right? Because that's how Gale-Shapley works. Y. At that point, Y prime must be, so either at that point or at a subsequent time step, Y prime must have rejected X because she got a strictly better partner, proposal, right? Must not at that point. Now, without loss of generality, I can assume that this is the first time, okay, that anybody is basically rejecting their stable matching partner, or rather, assume. So up until now, all the proposals that have gone on, okay, nobody would have rejected. Uh, uh, okay, let me just state this a little more. Okay, so I'm using a bunch of different notations. Sorry about that. So this means in the excess preference list, Y prime is ranked above Y. Okay, and so this is the same thing. So that and let me write it and then I'll explain. Okay. Okay. So it's clear that for Y prime, both X, this is X, and whoever this is, both are matching partners in some stable matching, distinct stable matching. This is a partner under M prime, and this is her partner under M. So people like this who are, who does anybody, a vertex, it may have multiple different partners in different stable matching. They're all called stable partners. So what I'm saying is, let's suppose, and this can be assumed without loss of generality, that the first time when Y prime rejects X, it is the first time when somebody is rejecting a stable partner in favor of somebody. Okay, so it Y prime may not be rejecting X because this person came along. It may be other people who are between them, and then eventually she ends up with this person. That's possible. So all I'm saying is, this is the first time in the entire execution of the algorithm that somebody has rejected one of their stable partners. Okay, all right. Now, can you see where the contradiction may emerge? Yes, these proofs are like this. It's slippery. They're not complicated, they're slippery. So, okay. So suppose, okay. So from Y prime's perspective, let's look at what might be motivating Y prime. Okay. So there is somebody here, okay, for who proposes, and therefore she rejects this person X at that step of the execution E, right? Now, what can that mean? That should mean that from this point onwards, this Y prime will either remain with this person or get somebody even better. correct? That should mean what? That X, well, X has been rejected by Y. So now X has been rejected by Y prime. So X will go down its preference list, right? That much is at least clear. So, however, there is a cost to pay. As in, M prime is a stable matching, so is M, right? But both women, so this woman is, okay, okay, let's say, whoever this man is, M. Can you see it? Is it? Okay, let me not write it as a statement. What about this? M. So is it clear which edge I'm referring to here? Y prime's so-called better partner than X. So whenever you see things like this, you should immediately ask, why isn't Y prime and that person forming a blocking pair with respect to M? If you think about it, try to finish this argument. Okay, if you cannot, after for the tea break, ask me. Okay, so finish this. It's not complex, it just needs to be stared at for some time. Okay, all right. So it can be shown, and it's you'll see that this essentially what it means is the ordering of the people. It doesn't matter who propose. You can randomly pick somebody, and this. It is very different from the Pareto optimal matching that we saw yesterday. When we were doing serial dictatorship, I said you call somebody and let them choose their best house, and just do assignments like that. It will result in a Pareto optimum solution. Its size-wise, it may be very bad, but it would also be maximal, it would be Pareto optimal, and so on. But here, we will next see, and this is the most remarkable result and the most stunningly named result, called the rural hospital theorem, which says that in any given instance of a stable marriage problem, the exact same set of vertices will always be matched. They are not matched to the exact same people. Okay. The set of matched vertices will always remain the same, even though there can be exponential number of stable matchings. Yes. So what is the most obvious consequence of this? The size remains fixed, right? Correct? So this is the marvelous thing. So the reason it's called rural hospital theorem is because, as I said, that for initial test case was the New England residence matching program. As is the case in most countries, assigning doctors to rural hospitals or hospitals which are not in and around urban centers is rather difficult, in the sense that they often have several open seats, they're always very understaffed. So they were wondering, if we didn't use this algorithm, if we used a different stable matching algorithm, can we increase the size of the assignment? Can we give those rural hospitals more staff or better, higher ranked, better quality staff? It turns out that that is impossible to do as long as they were using a stable matching algorithm. And that's the genesis of this name, rural hospital theorem. Meaning, if in one stable matching they go understaffed, they will be understaffed under every stable matching. And not only will they be understaffed, they will get the exact same set of assignments. So we will be proving this only in case of the one-to-one scenario. But if you understand this, you will be able to use it for the many to one case where I will state the theorem and leave it at it. So is the theorem clear? So not only does the non-deterministic guess of who goes first give you a different outcome, it also doesn't give you a better outcome. So it's remarkably robust. Okay? All right, so let's prove it. How am I doing time-wise? Okay. Sorry? 20 minutes. Okay. All right. So this is, can I write here itself? All right. So basically, let's say what? X is unmatched in, so M and M prime are two stable matchings, okay? X is matched in one and X is not matched in the other, okay? So let's just do some diagrams, drawing, and we will see actually it works here. So X is matched in M prime. No, what did I say? X is matched in M, not in M prime. So this is the M edge, okay? So now, as I said, X prefers being matched to not being unmatched, okay? So this is Y. What should be Y's preference when it's comparing M and M prime? It should prefer M prime over M. Can you say why quickly? This arrow means this. Otherwise, X and Y would be a blocking edge for M prime. It's that crossing thing that we were discussing. If the man prefers one matching, the other woman must prefer the other one. Otherwise, they will form a blocking pair. Okay. So similarly, X1's M prime partners, the matching prefers M prime. So for the same reason as in avoiding blocking pair, in the M matching, X1 should, if between M prime and M, X1 should prefer the his partner in the M matching. Okay, so these arrows are indicating that it's this arrow direction saying that, okay, X prefers this partner. X doesn't have any other partner, but okay. So Y prefers X1 over X. So that's what this arrow is indicating. X1, when comparing Y and Y1, must prefer its M partner. Otherwise, this edge will block stable matching M. That cannot happen. So if we continue like this, because of the finiteness, because we're dealing with a finite instance, right? At some point, we have to come back to X. You cannot end with an edge like this, because that vertex would be one where it is matched only under one matching and not both. And then the last edge that you get, looking at the direction, you will be able to see that it must be a blocking pair for the other matching. So to avoid that, it must be that it comes back here. But our initial assumption was X does not have an M prime edge. Okay. So this is the proof that every vertex that's part of one stable matching must be matched in every stable matching. Okay. So now I'll just say a few more things. So the marriage case was the simplified version of the hospital residence matching problem. It was a one-to-one setting. So the initial situation in which stable matching arose was the more generalized setting, which is, well, not the okay, the orderings are a bit off. Let me just say. So the test case was this one, many-to-one matching. This is like the standard job market, where an employee will only be employed by one firm, but a firm can have multiple employees. So it's like one association from the employee side, but the firms, so it looks like this, let's say. This sort of a thing. Okay, so this is also called the job market. So these are the workers and the job. Okay. This many to many is like from both sides you can be assigned. So this can also be a certain type of a job market. It's like when one worker is not a full-time worker for one firm, but they split their time across firms, maybe freelancing on temp working and so on and so forth. But there are other sort of examples, for, I suppose, for this also. The other case would be a non-bipartite graph. As I said, the definition of stable matching does not rule out the possibility of the graph being arbitrary. Hmm. Very good. And when can we do that? Yes, we can do that in certain settings when these companies have an upper bound on how many employees they will take. So the job market usually, no company can take everybody it applies, right? That many to one thing also has a constraint. So this basically also becomes like a capacitated matching. There's a capacity constraint on how many different edges can emerge out of one particular job, let's say. In hospital case, you can think of staffers. Some hospitals are big, some are small, they have different requirements and so on. So there's an upper bound. There has to be an upper bound, right? Sometimes there's also a lower bound. When you have only an upper bound, you can do what you're saying, and that's called the cloning. You basically clone this hospital this many number of times as its capacity, and then run Gale-Shapley, either from the resident side, this side or this side. Depending on which side you run, it will be in the real market, they run it from sort of the resident side, like from the worker side, but okay. But it will be a stable matching even if you run it from this side, okay? When you have a lower bound, lower quota basically says this job, this company has to get at least this many workers to keep functioning. So any stable matching basically has to give it at least that many number of assignments. And of course, it should not exceed the upper bound. So that becomes a feasibility question as much. Like you have to find that many number of which matches the upper and lower bound, and it must be stable. Okay. Now you should ask here, when the job market, when the employers are taking in groups of people, how is their preferences rated? Like how are they comparing between groups of people? It turns out that their preference is also like a ranking on the individuals. From there, there's a way to infer a ranking over groups of people. The most standard way of doing that is called responsive preference. So if two sets are identical except for one individual, okay, so these two are exact same, and this is one person, say P1, and this is person P2. And because they have a rank preference over individuals, this hospital or job will be able to rank this group, will be able to compare this assignment versus this assignment based on which one it likes more, P1 or P2. Because all these other people are same. So this sort of preference is called responsive. It does not necessarily have to be like this, but this at least allows us to somewhat succinctly represent the group preferences of the many side. Otherwise, their preference would be like listing subsets of all the candidates, right? That would be like a exponential size preference ranking. So anyways, so there are ways to capture these sorts of things. So the notion of stable matching in this case slightly changes, but essentially it remains the same as what we have discussed. So the other case is that of when the underlying graph is a non-bipartite graph. The question of whether there exists a stable matching, we know simply by looking at it. Here, so A prefers B, B prefers C, C prefers A. Can there be a stable matching here? It's a non-bipartite graph, right? There cannot be a stable matching here. So in very simple cases, also, unlike the bipartite case where we always have a stable matching, and Gale-Shapley will find it, in a non-bipartite, in the arbitrary case, we need not have a stable matching. So it was not until the 1980s, late 80s, by these individuals that it was shown Gusfield and Irving, yeah. So that they came up with an algorithm which is a far more extension sort of it extends Gale Shapley, the way Gale Shapley works, into one where given an instance of a non-bipartite graph with strict preference list, if there exists a stable matching, it will be able to find one, and in polynomial time. So that was a major breakthrough. Okay. The other case is this existence of ties in preference lists. So I have been talking about strict preferences. When we have ties, it's not clear how one would do these proposals, right? Okay. So now, uh, okay, so I have already said this. This is good. So let's look at the what the rural hospital theorem actually says in the many-to-one setting. It says that the set of people who will get matched on either side will always remain the same. If some hospital is undersubscribed, meaning it doesn't get it upper quota number of assignments, then the set of people who get assigned will always be the same in every stable matching. Okay, so it's much more than what we said in the many-to-one, in the one-to-one case. But using similar ideas, you can prove this also. Can't you read? It's there also. Okay. So now, when we have stable matching in the presence of ties, rural hospital theorem no longer works. Okay. And there, first and foremost, can you tell me what should be a reasonable definition of stable matching when there are ties? The blocking pair definition I gave very much relies on the fact that I will be able to compare my M partner with whomever, right? Everybody should have a strict, like it is a total ordering. Every two persons are comparable. But when we have ties, what we are saying is there are some individuals for whom I'm indifferent. So like if I am I'm an employer, HR manager, I like two candidates that are equally good. I really don't mind who these two people, whoever gets assigned. I only have position for one, and therefore I'm going to take one, but I don't care who. So in that case, there are several different notions of stability. The one that is sort of is closest to our is weak stability. Okay. It is defined exactly the way we said. Weak stability is one where there does not exist any strong blocking pair. What is a strong blocking pair? Exactly as we have defined. So A comma B is such that A prefers B more than its M partner. So it's not that A is indifferent between B and its M partner. A happens to strictly prefer B over its M partner. And B also returns favor and this. So this is a notion of a strong block. Like this is a really difficult, a matching simply cannot have this. So that's why it's called a strong blocking pair. If you don't have a strong blocking pair, you have weak stability. There are notions of lesser, more relaxed blocking pairs and correspondingly stronger and stronger notions of stability. Okay. So now we'll be talking about weak stability only. When you have ties, can we do something with Gale Shapley? Can we come up with any stable matching that matches this specification? Okay. So you are saying how to modify Gale Shapley, right? So suppose the men are proposing. So in the men's preference list, he is looking at a tied group. Suppose there are two women whom like this. So he breaks ties arbitrarily and proposes to one of them, any one of them. Okay, and suppose, okay, so then that from the men's side, it's clear, break ties arbitrarily when you're proposing. What should the women do? Okay, she doesn't reject the current partner. Okay. Okay. So that, okay, and so she only rejects, but she gets a strictly better thing. Okay, that will result in a weakly stable matching. Do you see why? Because literally you're not going to, you're not the same reason why which the normal Gale Shapley was correct is the reason, because the definition of you never reject unless you get somebody strictly better. And holding a in the same tied partner is not going to lead to a blocking pair. So that will give a weakly stable matching. In fact, you can break ties arbitrarily before starting a proposal, okay, and then run Gale Shapley. What you were saying is like dynamic. In the run of the algorithm, you're breaking ties, right? So that will result in a stable matching, but it may not be the maximum size stable matching. Because rural hospital theorem does not work anymore, we know that there can be stable matchings of very many different sizes. Can you very quickly tell me how different can they be in size? How far away can you be from the maximum size stable matching? Quickly. The first property we saw about stable matching is what? No, even before that we saw some, okay, no blocking is the definition. After that we proved a property. Yes. So all stable matchings are maximal. Whenever you have that, you should know two maximal matchings can only differ by size. Two, like one can only be half of the size of the other. So by breaking ties arbitrarily, at least you're guaranteed that you will get a half approximation solution. You may not get the maximum size stable matching, okay, but you will get at least half as much. Is this clear? So for a while, for a long time, people wondered, can that half bound be broken? Okay. And so in 2008, Kirali gave a really ingenious algorithm, which I will just repeat, and the proof is really that simple. For the purpose, it's a bit easier if you just assume that from the men's side, there are no ties, let's say. Only the ties are on the women's side. So the men's side is this A, and the women's side is B. You create this two-layered graph where the male vertices get replicated at 0th level as they are, and then at the first level. Okay? They retain their preference list exactly as they were in L. Okay? So it's also a type of cloning only. From the B side, from the women's side, they will use the same preference list as they were using in L, except that they will rank the the A vertices from the level 1, all of them before the 0 level. So this is how it will look, okay? So every edge in the given instance will now be represented as two edges. So the 0th version of A with B and the level 1 vertex of A with B. And the same preference list for B, she will by default rank the first level person more than the 0th level person, okay? And the rest of the preference list would be B's preference list as was before, but put all the level 1 vertices before level 0 vertices, okay? And now you run Gale Shapley. Here, again, the rejections will happen when, so if two zero level vertices are proposing to this woman, she will see who she likes. If she has a strict preference for one, she rejects that, and just the way Gale Shapley works. Okay. Now, quickly by looking at this two-level idea, can you tell me what is it actually trying to do here? So, okay. So first and foremost, the way the proposal works is here, you don't let anybody propose at any order. The zero level vertices will propose first. If they find a matching partner, then that's it. If A0 gets rejected by everybody, then A1, the level 1 version of A starts proposing. Now, because level 1 version of A has a higher priority for in each of its neighbors' preference list, right? So whoever he proposes to, unless she's already holding a proposal from a first level thing, if she's currently holding a 0th level, a proposal from a 0th level, she will reject that and move on to the first level. Okay, so this is like giving a second chance, running Gale Shapley in a sort of tangled couple way twice. Okay, so it turns out that this simple algorithm will result in a 2/3 approximation. So I'm just going to take 5 minutes to go over this. This exemplifies a very simple trick in all matching type analysis, which all of you should know. So tell me, how should this proof begin? Okay. I've already given, this has become mangled. Sorry. Yes. Tell me. So what should be the first step? We are claiming, let me just write here. This, so that algorithm was given by Kirali. Okay. Output M is of size at least 2 by 3 of M opt. What is M opt? It's the maximum size stable matching. So whenever you see this, you should always think of comparing the two matchings. The two matchings comparison means symmetric difference. You know what's a symmetric difference? You look at the set of edges which are in one matching but not the other. So let's see. Okay, it's actually written here. So this is what the notation is. Please know it. And always, whenever you see two comparisons of matchings, or in fact, any two sets, you should always think about what's in this and what's not in this. Notice the reason M is not equal to M opt size-wise must be because there must be some edges in M opt that are missing in M and vice versa. Right? Because M is at least maximal. So there must be some edges in M. So M cannot be a complete subset of M opt. Is this clear? No two maximal matchings can be a subset of the other. This is why looking at symmetric differences, like there is something in M opt that's not in M, some edges in M that is not in M opt, okay? So here, now can you tell me how do the edges in this, if I just looked at this edge, these edges, how does the graph defined on these edges look? You all have done a course in graph theory, haven't you all? Matching, I mean, okay. If you've done a course in algorithms, you must have done a course in graph theory and seen. So, okay. So this thing consists of vertices that either are matched in M and not in M opt, right? But if they're matched in both, then they have different partners, correct? Or they are only matched in M opt, but not in M, or they're matched in M and not in M opt. So what can we say about the degree of these vertices? At most 2. So what can we say about graphs on vertices that have degree at most 2? Cycles and paths. Here also the same thing, cycles and paths. What kind of cycles and what kind of paths? See, the edges only come from M opt or M. They don't come from the intersection. So the cycles and paths consist of alternating cycles or alternating paths. Every edge, if you look at the cycles must be even length, because this is M opt M, M opt M. You have equal number of edges, or you have paths. So let me draw the paths like this. So you can have a path that starts with an M opt edge, has an M, then M opt edge, then M, and so on. So in this is M. This is what one would, this is an alternating path. But notice here, it starts with an M opt edge and ends with an M. Whenever you have these sorts of things, paths, you can count and see they must have equal number of M opt edges and M edges, right? Okay. Now, if I have a alternating path that starts with M opt and also ends with M opt, then what can I say? Size-wise, what can I say? Right. So this is what I would call a M augmenting path. Okay. The ym, basically the two endpoints are unmatched by m opt, are matched by m opt but not by m. So these sorts of paths are called m augmenting paths. Similarly, you can also have m opt augmenting path, right? There, the number of edges of m will be greater than that of m opt, correct? So these m augmenting paths have odd size, let's say 2k plus 1, of which m opt contributes big k plus 1 and m contributes. So the fraction is this, correct? Right? Now notice I'm only trying to compare the size of m opt with m. The portions that are common in the two, they are of no consequence. This is why I'm looking at the symmetric difference. M opt must be picking up more edges than m is. If they were picking up equal number of edges, right, I would never have an m augmenting path because alternating cycles are even length. They have equal number of m opt and m. So if I have to see the difference in size of m opt and m, I basically should be counting the m augmenting paths. Is this proof scheme clear? If nothing else, you should take away this idea that when you see two matchings or generally any subset, two subsets of something, and you're trying to compare size, you should think about symmetric difference. And this particular idea finds its most finest and most sort of continuously useful exposition in the world of matchings. So what is it that to get the 2/3 bound, what do I have to show then? K by k plus 1. How large is it? Isn't this at least 2 by 3 if k is greater than what? 2? Right? So I automatically get this. So every m augmenting path, okay, will meet this, will give me 2/3 fraction of more m augmenting m opt edges than m edges. How many m augment, no matter how many m augmenting paths I have, each one gives me that 2/3 fraction. So overall, I have a 2/3 fraction more of m opt edges, right? Now that's true if I can show that k must be at least 2 or more. So for this whole idea to work, I should prove that no, very good. Therefore, no three sized m augmenting paths exist. So now you all can go. This is actually true. Pallavi, how much overtime have I been? I'm sorry. Okay, I'll stop it. Please try to prove this for those of you who are interested. Again, it's a bit like the type of argument that we were. Here, you have to be mindful of that algorithm, that level-wise proposal, and so on and so forth. Okay? But this is it. And that gives this 2/3 bound. So I'm going to stop here. Okay. Thank you. All right.